Let us look now at another proof, the proof by Pitman, that uses a combinatorial idea. So we want to prove that the number of labeled trees on n vertices is exactly n to the power n minus 2. So call this number Tn. We want to show that Tn is exactly equal to n to the power n minus 2. Actually, we'll prove that n factorial times Tn is equal to n factorial times n to the power n minus 2. For some reason, this will be easier. So n factorial, remember, is the product of all positive integers up to n. If we manage to prove this, well then, just by dividing by n factorial on each side, we will have our theorem. So this is now what we want to prove. So how do we prove that these two numbers are equal? Our strategy is to show that both numbers count the same thing. Namely, we want to count the number of ways that you can start with the null graph on n vertices and add directed edges or arcs so that what you get is a rooted directed tree on n vertices. So before we start with the proof, a couple of remarks. First of all, these directed trees have nothing to do with Cayley's theorem. It just so happens that these two numbers we're looking at are ways to count these things in two different ways, and we can use that because these numbers are related to the numbers we are interested in. And also remember that a rooted directed tree is a tree where you have chosen one vertex as a root and directed all edges away from the root. So go back to that lecture if you don't remember this. So in this case, we have this root and all edges are directed away from it. Also, one more thing to remember is that we're not counting the number of these actual trees. We're counting of the number of ways of building them. So for us, what I did here, I put this edge first and then this edge second. That would be different from putting this edge first and this edge second. So it's like I'm not counting the number of ways that roads can be sitting in a city. I'm counting the number of ways in which a city can construct roads. So maybe they construct road A first and then road B. Or they construct road B first and then road A. The result is the same, but since I'm not counting the result, I'm counting the number of ways to achieve this. These will be two different numbers of ways. So we will now count the number of ways to add directed edges to the null graph on n vertices and no edges until we obtain, as a result, a directed tree on n vertices. So we will first look at things from one perspective and show that in fact there are n factorial times Tn ways to start with a null graph and add edges so that you get the tree you want to get. We'll look at the general algorithm first and then see how it's done in a simple example. So how do you construct such a tree? Well, first you choose which undirected tree will be the underlying tree of this rooted directed tree that I want to construct. Second, I choose which edge I want to be my root. And third, I choose in which order I'm adding the n minus 1 edges. So let us look in the case of n equals 3. So I have these three vertices. First, I decide which, so here I have vertex 1, 2, 3. Everything is labeled here. So first I decide which edges will I actually want to construct. Where do I want to draw my roads? Let's say I would like to have this edge and this edge. Okay. Then I decide, okay, which of these three vertices is going to be my root? Well, let's say this one is the root. Then in which order do I add the edges? Let's say I want to add this edge first and this edge second. And of course, since I have chosen my root, the direction on the edges is automatic. That is not something I get to choose. The root dictates that this will be a one-way street in this direction and this will be a one-way street in this direction. So in how many ways can this be done? Well, first of all, how many undirected trees can I have? That's Tn ways. So the first choice I did, the choice of possible underlying trees, the choice of edges to be constructed in my tree, this can be done in Tn ways. Then I have n vertices, and so I have n ways to choose which vertex to be my root. Then since I have a tree on n vertices, it's going to have n minus 1 edges because one edge less. So since I have n minus 1 edges, I have to choose which one to add first, which to go next, which to go next, and so on. And as you probably know, the way of ordering n minus 1 objects in a defined order is n minus 1 factorial, the number of permutations. So since these three choices are independent of each other, my total will be the product of these. So Tn times n minus 1 factorial. So n times n minus 1 factorial, this is n times n minus 1 times n minus 2 down to 1, and I get n factorial times Tn. So this shows that there are n factorial times Tn ways to place edges so that I obtain a rooted directed tree from n labeled vertices. And that is our first way to count these construction ways. Okay, so now somebody comes in and says, no, this is stupid. This is not the way to count how many ways to do it. I know a better way to count that will show you that there are in fact not n factorial times Tn, but n factorial times n to the power n minus 2 ways to do it. So how is this done? This is done by adding one directed edge at a time. So let's look at the general algorithm and see how it works in our small example. So at each step, you're adding one directed edge just right away. You don't plan ahead or anything. So you start with your n vertices. At the first step, you add one edge somewhere. At the second step, you already have an edge. So you now need to add the second directed edge in a good way, and so on. At the kth step, you have already k minus 1 edges there, so that you have a forest of rooted directed trees, and now you need to add your kth edge so that it remains a forest of rooted directed trees. And here's the way to do it. So let's illustrate this. So at step k, before you do the kth step, you have something that looks like this. Maybe something like that, or yeah, let's say you have something that looks like that. Why does it look exactly like that? Well, actually, it's because of the way the step is defined. So it's inductive. So now we will see that our way is coherent with this way of seeing it. So now I want to put my kth edge, but I can't put my kth edge randomly. For example, if I put my kth edge like this, this won't work because now where will my root be? I'm not having one unique root from which everything goes away, because here you see here you have a sequence where these two collide. It's not the way a rooted directed tree works. So here is the way to add your edge. So before doing that, I realized I forgot to draw this arrow. There we go. So now if I want to add an edge, it can go from whichever vertex I want. So let's say I wanted to start from this vertex. So I have n ways to choose my starting vertex. Now I cannot go to any vertex on the same component because that would create a cycle, and so it won't be a tree. It will create multiple, the underlying graph will not be a tree because it will have a cycle. So I have to go to a different component in order not to create cycles. And I have to go to the root of the different component. So I'm assuming that I already have rooted directed trees. I mean, it's clear from this picture, but here this is the root of this tree, this is the root of this tree, this is the root of this tree. So these are the roots from which everything goes away in these trees. And now by adding an edge, I have to go from any vertex I want, but to a different component and to the root of a different component to keep this flow of everything going in one direction and to avoid these clashes that I had earlier. And at stage K, before I put this red edge, I had the number n minus the number of edges I have already put. So I have n minus k plus 1 rooted trees. So we talked about this in the beginning when we talked about trees, how many edges a forest has. So, and how many components a forest has. So in our case, since we have k minus 1 edges, we have n minus this number of edges. So this results in n minus k plus 1 components. Think about this and compare this to the thing we said before about forests. So now starting with this number of components, since I have n ways to choose a starting vertex, and I need to go to a different component and to the root of that different components, since there are this number minus 1 different components, I have n minus k different components, and so I have n minus k different roots. So in other words, at step k, I add an edge going from whichever vertex I want to the root of whichever other component I want. And now I have one edge more and one component less, and I can do step k plus 1 and so on until my step n minus 1, where I put the very last edge and create a tree altogether. So how many ways can this be done in? Well, at step k, I had n choices of starting vertex and n minus k choices of ending vertex. So I have n minus k times n choices of putting this k, this kth edge. So the kth edge can be put in this many ways. And this is true for all k, and all choices are independent of each other. So to get the total number, I will multiply this for k going from the first step, k equals 1, when I had no edges and I put my first edge, and step n minus 1, where I put the n minus first and therefore last edge of the tree. And the rest is just simplifying this product. So this is n minus 1 times n minus 2 times n, etc. until we go to 2 times n, 1 times n. And if you simplify, this is n minus 1 factorial times n to the power n minus 1. So this is n times n to the power n minus 2. And I bake this n into the factorial and get n factorial times n minus 2. This was a complicated way of counting how many trees I have, but still it's a way of counting these trees. Don't worry if you did not accept or follow all these steps. That's not the important thing. The important thing is that now I have shown you 2 ways to count the number of ways to construct such things. And since the first number of ways was n factorial to the power n factorial times tn, and the second way was n factorial times n to the power n minus 2, since I was counting the same thing, namely the number of ways to construct from a null graph a rooted directed tree with n vertices, then these numbers must be equal. So Tn must be equal to n to the power n minus 2, which I get by cancelling out these n factorials. So let me repeat what I said in the beginning. We're counting ways of constructing trees, not trees. And these things we're counting the ways of constructing, they have nothing to do with Cayley's theorem so much. They're just a convenient gadget that we can count in two ways, where one of the ways involves this number Tn that we want to know something about. That's the whole idea. So now we have shown that these numbers are equal. So what is now the philosophical remark? There is always a philosophical remark. The philosophical remark is that this idea of counting the same set of objects twice and get different formulas is a very useful way in combinatorics to show that two numbers are equal. So combinatorialists like to count, and if they can count the same thing in two different ways, then they are happy because they know these two numbers are equal. And the gain is, apart from knowing the numbers are equal, you get new perspectives. In this way, if we were actually interested in counting such ways of constructing trees, now we got two ways of doing it. And we got a relationship between two numbers, or two ideas really, that we didn't see before. But now, since these two ideas help us count the same thing, we know they are related to each other. And this is a useful method in combinatorics. So now we have seen the two proofs of Cayley's theorem. Proofer's constructions you are required to remember. Pitman's proof, if you didn't follow the details, it's not a big deal. But if you're interested in combinatorics, I encourage you to go deeper into it. There is a third proof in the book, if you'd like to look at it. And there are more proofs that you can find online of this theorem. And it's amazing how one theorem can have so many proofs. In some way, it's telling you that the theorem really brings something new, because you can view it from different angles and prove it in different ways. This was a philosophical meta remark, and with this we end the lecture.